welcome in the second part of the mechanical properties of solids lecture series. In the last video, we have discussed about the basic concept of elasticity of the materials which have the property to regain its original shape and size. And also we have discussed about the different kinds of modulus. Out of them, one was Young modulus of elasticity for such type of bodies which undergoes in the length contraction or compression. And second modulus was discussed, that was bulk modulus of elasticity for such type of bodies which undergoes the volumetric strains when they are accounted on exerting the normal stress. Okay, and another constant of elasticity was shear modulus of plasticity eta, and the last one was the Poisson ratio sigma. So in the last video, that was the first part of the mechanical properties of solid, and this is the second part of the same series. Okay, so in this video, in the second part of this lecture series, we are discussing about the relations among elastic constants which was discussed in the earlier video. And how many relations were they? They were by Young modulus of elasticity, and K bulk modulus of elasticity, and eta shear modulus of elasticity, and rest is sigma Poisson ratio. Okay, so in this video we are going to characterize the relation among all these four constants in different ways, taking one consideration of this cube. Okay, so let's start to derive the relation among them. Before begin of the relation consideration, I would like to concern here one thing, that is the compressional strain and extension. In what conditions we use bi for the extension, and in what conditions we use Poisson ratio for the compressional strains as well. So first let us take a look for them. Okay, so you have to remember two things when you come across related to the elasticity. One thing is, if there is a extension in length or any other dimension, then we use the Young modulus of elasticity. Generally, Young's modulus of elasticity is taken for the extensions in the bias or the extension in the all kinds of dimensions. So whenever there will be a extension, I will take the use of bi. Okay, and what about the bi? Bi is nothing but generally stress over strain. If I take this bi for a particular dimension like length, then I will take here stress like there is any type of stress. Let's say this is a pressure generally P, and divided by this is strain for a bi. This is delta L over L, where delta L is the change in dimension, increased dimension, and L is the initial dimension like length. So whenever there will be extension, I will take use of bi. Okay, another consideration is whenever there is a compression or contraction or compression, we should use Poisson ratio. Okay, so what about the Poisson ratio? Poisson ratio was the strains ratio of different kinds of conditions, and this was the lateral strain over longitudinal strain. So this is what we have discussed about the Poisson ratio. And what is the lateral strain? Lateral strain is just related to the area. Okay, in the last video we have taken the lateral strain as diameter strain, so that was delta D over D. This is for lateral strain. And longitudinal strain is nothing but the change in length divided by original length, and this is sigma. This also can be viewed as delta D over L, delta D over delta L multiplied by L divided by capital D. Okay, so this is what we have, this Poisson ratio, and there was a minus also here, which is showing the contraction in any dimension, any one strain, okay, and that is the contraction in the lateral strain in the last case, what we have discussed in the last video. Okay, when I shall discuss about the relations among elastic constants for this particular cube, then there will be a contraction in one edge. We will discuss later. Okay, so I will take the Poisson ratio here, and when I will take the Poisson ratio here, that in that condition, you also can relate this formula with the normal stress. Okay, if there is a normal stress, then that is related to by equals to P over delta L over L. This is a Young's modulus for such a wire which is undergoing in the normal stress P and stretching up to delta L, having initial length L. So this is for that particular case. You can also see here that I can take in the place of delta L over L as P over by. So whenever I will see delta L over L, I can replace that particular ratio by P over by. So just remember this thing here. So I can take use of this value in this expression also. So this is sigma, and this is delta D. This is delta D over delta L over L. So delta D over D divided by delta L over L. Okay, and delta L over L is going to equal P over Y from this consideration. Okay, so this is P over by here. This is P over by. So I can take use of sigma times of what? Sigma equals delta D over D multiplied by over D. Okay, sorry, by over P. So this is what we have, the relation between the Poisson ratio and the Young's modulus of elasticity in terms of normal stress and the lateral strain here. You can easily see this is a cube, and the speciality of the cube is that it's all the edges have the same length, and I also have marked this, each edge is L. Okay, so each edge, all the 12 edge of this cube as L. So whatever be the contraction it's in its any length, that will be also as L. Okay, because all the edges are L. Some edges will contract, some edges will be extended. When we will apply the normal stress on the surface of this cube, then all the contraction and extension will be for length. So here I will take delta D over D as also L, okay, for this cube. So this is delta, whatever this is the value, this is delta L over L here also. So this is the contraction, because I am taking the context of Poisson ratio, and I have told you that whenever I will take the contraction, I will take the help of the Poisson ratio. So delta L is the contraction in any one dimension. So this is the delta L, which is equals to sigma times of L, sigma times of delta L equals to sigma times of L multiplied by P divided by. So this is what we have, contraction in any dimension of a cube. So this is delta L. This can also be written as in the simple words like P over by sigma times of L. I will take use of contraction in length as delta L, and extension in length as simple from this formula. Extension in length, this is delta L equals to what? P over by times of L. So as far as the extension is concerned, I will take the use of delta L equals to P over by times of L. And as far as the contraction in the dimension is concerned, I will take the use of this sigma times of P over by and L. Because whenever there is a contraction, Poisson ratio should be mentioned. Okay, so Poisson ratio is mentioned in such places when there is a contraction in any dimension. Okay, so these are the two formula I am collecting with this board, these two formulas. This is a sigma P over by times of L. So the particular difference you can check here. This is for contraction and this is for extension. So for extension, P over by L is taken, and for contraction, sigma P over by times of L is taken. Okay, so let's begin to derive the relation among the elastic constants. Okay, so now you can check on the board the respective diagram. What I will take the use of this diagram. So you can see this blue marked cube has been taken in such a way that it's the lower face is on the x and z plane. This is the lower face of this cube. This is in the x and z plane. Okay, this is x axis, this is z axis, this is y axis. Okay, so this is a lower face along or lying in the x and z plane, and it's this face. This face is lying in the y and z plane, and it's the backward. It's the back front is taken in the x and y plane. Okay, also we can easily see that it's all three Cartesian coordinates axes are taken along the edges of this cube. Okay, for the convenient I have marked each edge of this cube is small l. Okay, so let's start to know the relation among the y and all these considerations, coefficients. So first we will derive the relation among, let's say, y, k and sigma. So first we will derive the relation among these three constants. Okay, so for that relation I am taking a simple example of this cube. And what is that? Suppose that this is a cube, what you can see on the board, and it is undergoing by a normal stress P from all its faces. You know very well there are the 6 faces having by a cube. Okay, and all these 6 faces are undergoing by a normal stress P. You can easily see that this is the one face undergoing to the P normal stress. Normal stress is said in that construct. This is the perpendicular stress of the surface. Okay, this is a surface, this is the perpendicular stress. This is the surface, this is the perpendicular stress. Okay, now another face which is along to the negative x-axis is also undergoing to the same stress, same normal stress. Also, this is the upper face of this cube is undergoing the P, same normal stress. This is the lower bottom face of this cube is undergoing to the same normal stress, and this is the front face is also going to the normal stress P, and the back face is also undergoing to the same normal stress as P. Okay, so we will take one by one all the contractions and extensions along x-axis, y-axis, z-axis respectively. So first I am taking this normal stress which is along the x-axis, whatever it is positive, whatever it is negative. Okay, so when I apply this normal stress along x-axis, then there will be an extension along the x-axis, because this is a normal stress along the x-axis. So this face, this edge which is along the x-axis will be extended on the course of this P. Okay, and in that particular condition the extension along x-axis will be what? According to this formula. Okay, so this will be P over y times of L. What is P? P is a normal stress. What is L? L is the edge length along the x-axis which is extending on the account of P, and this is the y. This is a Young modulus of the material of this cube. Okay, now when you apply the normal stress along x-axis, I am taking the consideration along the x-axis normal stress. Okay, if you use you see the microscopic phenomenon. When you apply the normal stress along the x-axis, then simultaneously y edges which are along the y edges will be contract, because you are extending in this way. Y axis will be contract as well as z axis will be also contract. You can easily feel this in the real phenomena. If you are stretching a cube along the x-axis, then what will happen? it is contracted in this way as well. So I am taking the same. This is the normal stress along the x-axis. What will happen on the account of this normal stress? Its y edge will be contract as well as its z edge will also be contract. Okay, so there is an extension along x-axis which is according to this formula, and there is also compression or contraction along y-axis as well as z-axis, and each contraction along y and z-axis can be shown by this formula. This is sigma times of P over Y times of L. Same contraction will be along the z-axis. Okay, so if I am interested to find the net extension along the x-axis, then what will be that? That will be net extension. Net extension along x-axis, that will be total extensions plus total contraction. Okay, so total extension is P over Y times of L. These are the contractions, so I will take as a negative them. So these are the sigma minus sigma P over Y. This is because this is the decrease in the length, as well as this also is a decrease in the length. So this is the net extension along the x-axis. This is positive because this is extension. These are the negative because these are the contraction in the edges. Okay, so by rearranging the terms, you can take common as P over Y, because P over Y times of L is appearing in all the three terms. That can be taken as common. So this is a P over Y times of L, and this is the 1. These are the two factors. So sigma and sigma becomes 2 sigma. This is what we have final extension. Now I will take the same consideration for the y-axis. Now I am considering this normal stress. This is along the y-axis, along the y-positive axis as well as along the y-negative axis. What will happen? All the considerations and fact will be same as these are for the along x-axis. Okay, so similarly I can use the word here that similarly the extension, net extension along z-axis, taking the same consideration for that particular normal stress along the y-axis, along the y-axis, what will that will be the same net extension. This will be the P over Y times of L by minus 2 sigma, because all the normal stress are same. So the total net extension along the all three axes will be same. This is along the y-axis, and same along z-axis. Net extension along z-axis will also be same. That will be P over Y times of L and 1 minus 2 sigma. These are the three net extensions along x, y and z axis edges of this cube on account of the normal stress which are along to the x, y and z axis having the same value as P. Okay, so the net extension formula is this, which is the same for the three axes. Okay, now if I find the change in volume or final volume under these extension, then that what will be that? That will be change in volume, or let's say change in volume. Okay, so change in volume of the cube. So what was the initial volume? That was the L cube. And what is the final volume? Final volume is the simple volume is edge cube. And what is the edge? Edge is L. So this will be the L cube, initial volume. Now what is the complete edge now? That complete edge is, this is the initial edge, and there is a net extension of this value. So this is the P over Y times of L and 1 minus 2 sigma. This gives me the initial length. This is the extension in length, which is the final length or edge of this cube. Okay, after all the considerations. So this is the final length or edge of the cube. So this will give me the final volume. and change in volume is nothing but final volume minus initial volume. And what is the final volume? The final edge cube. So this is the final edge. This is the L plus P over by times of L1 minus 2 sigma. This is the final edge. I am taking it as cube because it's the L, this is the 3 power. And minus Vi. Vi is the initial volume. Initial volume was L cube because all the edges were L. This is what we have, change in volume. Mathematically, you can rearrange the terms again here. This is the cube, so that I am taking L as common from the both the terms. So as I will take the L as common, that will be come out as L cube, because this is the complete whole cube of this two factors addition. So this is a 1 plus P over by and 1 minus 2 sigma cube minus L cube. Right? Now I can expand these two terms power by using a binomial theorem, and you know this is a 1 plus x whole raised to power n form. This is a 1 plus x whole raised to power n, and that will be 1 plus nx plus n in nx and n minus 1 into x square over 2 factorial and so on and so forth. You can see easily that what x, this is the complete factor, this is the minute factor, and the power of these minute factor will be go increasing. So that will also be decreased. So I will take only these two terms in consideration which have only lower power of this minute term. So this is the 1 plus nx. So after opening this bracket, I will take 1 plus nx. N is a 3, x is this value. This is the 3p over by 1 minus 2 sigma minus L cube. So I have used here binomial theorem. Okay. Also you can multiply the L cube in the whole bracket. That will be L cube plus 3p over by times of L cube 1 minus 2 sigma minus L cube. This is cancelled by this L cube. Okay. Rest is 3p over by times of L cube and 1 minus 2 sigma. This is what we have, change in volume delta B. Okay. In order to define the bulk modulus of this cube, I will take normal stress divided by volumetric strain. That's why I have reached up to this volumetric change in the volume. Okay. So now I can define a constant for this cube. This is what is that? That is bulk modulus of cube, which is nothing but K. K is nothing but normal stress divided by volumetric strain. And what is the normal stress? Normal stress is nothing but P, which is the same for all the 3 edges, all the 12 edges, 6 edges, sorry. This is a P. Volumetric strain is nothing but change in volume divided by initial volume. So this is the P. This is the delta B. Delta B is this value. This is the 3p L cube divided by and this is 1 minus 2 sigma. This is the value of delta B divided by initial volume. V is the initial volume. What is the V? B is L cube. Okay. So this is what we have, bulk modulus of this cube material. Now L cube is cancelled by this L cube. This is going to equal K. Okay. So K equals, this P is also cancelled. K equals, this by will be in the numerator. This is by over 3 times of 1 minus 2 sigma. This is the final terms what we have got. So this also can be written as by equals 3k 1 minus 2 sigma. This is what we have, the relation among the 3 constants, namely by Young modulus, K bulk modulus, sigma Poisson ratio. So these are the by, K and sigma relation among the constants. So firstly we have derived the relation among by, K and sigma. Secondly, let's derive the relation among other constants. Okay. So for that particular consideration, I can use again this cube. Okay. Now I will take the relation among by k and eta. These are the three constants have a particular relation. Okay, so in order to find the relation among the three constants which are by and k and eta, I am taking the same cube but in different considerations. And what are the considerations? Let's check that. Now I am taking a particular case of this cube in which there is an extension, there is a normal stress along the x-axis which is showing by these two vectors, and there is a compression along y-axis which is showing by these two vectors. So in actual extension along x-axis, and there is a contraction or compression along y-axis. There is no any extension or compression along z-axis. This is a particular case what we are taking. So you can easily see that I do not have shown any normal stress along the z-axis. Okay, these are the free of any type of normal stress. Only there are two types of normal stress are acting on this cube. One is along x-axis, which is generating an extension because these are in the opposite direction in this way, and these are the two normal stresses which are generating the contraction along the y-axis. And why we are taking these two considerations, I shall discuss about them in the later time. Okay, so let's say in that particular case the complete extension or contraction. So extension along x-axis will be P over by and L, same according to this formula. Okay, and contraction along y-axis will be P over by times of sigma times of L. There is a contraction due to these two normal stress. Okay, now net extension along x-axis will be that. What will be that? That will be total extension P over by times of L and plus total contraction. For the contraction I am taking negative because the edge length is decreasing due to these two normal stress. These are the sigma P over by times of L. You can take common as P over by times of L and the rest are 1 minus this sigma. These are the next net extension along the x-axis. Okay, there is no extension or contraction along z-axis. Okay, now this is the case when I have taken the normal stress along the x-axis in this way according to these two vectors. Now just reverse the process. What I mean by the reverse the process, now take the normal stress along the x-axis in this way and a contraction, and an extension normal stress along the y-axis. Then what will happen? The same consideration will be taken for the y-axis, right? Because I have reverses the direction of the normal stresses along x-axis and y-axis as well. Then what will happen? The same net extension. Now there is extension along y-axis and contraction along x-axis. Okay, because these are the edges will be extended, these are the edges will be contracted. Okay, so net extension along y-axis, that was along x-axis, now this is along y-axis, that will be the same. This is a P over by times of L 1 minus sigma. Okay, now these two net extensions are doing a very important work. And what is that? Let's discuss that. So these are the same extensions. We have P over by times of, let me write here, this is P over by times of L1 minus sigma. Okay, these are the extensions, two extensions. Now if I am interested to find the longitudinal strain due to these two extensions, then what will be that? Longitudinal strain. Longitudinal strain will be delta L over L. And what is the change in the length? This is the extension, this is the change in the length. This is the P over by times of L, 1 minus sigma, divided by initial length. L is cancelled by L. This is P over by times of 1 minus sigma. What we have, this is the longitudinal strain. Okay, now you can observe that when there is an extension along y-axis, simultaneously there is a contraction along x-axis. There is an extension along y-axis, there is a contraction along x-axis. Now these two extensions do not take place, do not let take place to the z extension on contraction. What I mean by the z axis contraction and extension is that when this is the normal stress along the x-axis in this way, so there will be a, when you are pressing, you are compressing this cube along x-axis in this way, then there will be a extension along z-axis. Okay, and why it is that? Because you are compressing the cube, then there will be an increase in the z-axis length as well as in the y-axis length. Okay, now you are taking normal stress along the x-axis, compressing the x-axis, there will be a z-axis extension. Okay, but simultaneously you are applying normal stress in this way. So whatever the extension in the z-axis is due to the x-axis normal stress, that will be equals to what? That will be cancelled out, because I am pressing in this way, z-axis extension, at the same time you are extending the y-axis along this direction, then whatever amount of extension in the z-axis, that will be cancelled out by the extension along the y-axis. Extension along the x-axis, sorry, compression along the x-axis, extension along the z-axis, extension along the y-axis, extensions along the y-axis, that is equals to the z-axis. So there will no, after all, there will no extension or compression along the z-axis. This is the final criteria what we have. Okay, so both the normal stresses are taking place simultaneously, and due to that there is no contraction, contraction or extension along the z-axis, and this is happened only for the shear type of bodies. Okay, because no change along z-axis, and due to two mutual perpendicular what? Normal stresses along x-axis and along y-axis. This causes no change in the z-axis. Now I can take the use of these two longitudinal strains. So these two longitudinal strains, one is along x-axis, one is along y-axis, are generating a shear strain in the body, which do not let take place in the z direction. Okay. So due to these two perpendicular strains along x-axis, one is along x-axis, another is along z-axis, there is a shear strain which is created. Okay, so complete contribution of these two longitudinal strains is generated the shear strain. Okay, so I can take the use of both. This is a 2p over by times of 1 minus sigma, which is equals to theta. Okay, so now you can rearrange the terms. I am taking it as p over theta equals to pi over 2 times of 1 minus sigma. Okay, now you can easily see that this is the normal stress pressure, this is the shear strain theta. So normal stress over shear strain is nothing but shear modulus. This is the pi over 2 times of 1 minus sigma, and also can be written as pi equals 2 eta times of 1 minus sigma. So this is the another relation what we have. This is the relation between pi, eta and sigma. Pi, eta and sigma, sorry, is the sigma. Okay, there was the last relations what we have derived, that was pi equals 3k 1 minus 2 sigma. Okay, so these are the two relations among the elastic constants. Okay, so I think this is the good place to stop this video. In the next video we will look at the another properties of the solids. Okay, thanks for watching.